Hey guys, welcome back to my CCNA 200-301 course. Patrice is here, and in this video we are going to review dynamic routing basics. Are you ready? Let's get started. Let's start by understanding the difference between routed protocols, also known as routable protocols, and routing protocols. Two key concepts in networking. Routed protocols are responsible for the actual delivery of data across a network. They define the format and structure of the data packets and ensure they are forwarded to their correct destinations. Examples of routed protocols include IP version 4 and IP version 6. These protocols operate at layer 3 of the OSI model and focus solely on transporting data, not on determining the best path to take. On the other hand, routing protocols are used by routers to determine the best possible path for data to travel through the network. They exchange routing information that are called advertisements in routing terminology with other routers and build routing tables to make dynamic decisions based on network topology changes. Examples of routing protocols include RIP, OSPF, EIGRP, and BGP. A simple way to think about this is routed protocols handle the what data needs to be delivered, while routing protocols handle the how to get the data there efficiently and reliably. These two work together to ensure that data flows smoothly and efficiently across networks, even in complex environments. Now let's explore the basics of dynamic routing. Dynamic routing protocols play a crucial role in modern networks by automatically updating routing tables when the network topology changes, which is called convergence. Dynamic routing protocols provides flexibility and scalability. First, dynamic routing protocols dynamically update the routing protocol, ensuring that routers always have the most up-to-date path to a destination. Second, they determine the best route to each destination based on a metric. This metric is calculated using specific algorithms, and the complexity of the calculation varies depending on the protocol. For example, in a simple protocol like RIP, which stands for Routing Information Protocol, the metric is just the number of hops to the destination. Since RIP only counts hops or routers or the number of routers, it's classified as a distance vector protocol. In contrast, OSPF, which stands for Open Shortest Path First, uses a much more sophisticated metric. It calculates the cost of each link, taking into account factors like bandwidth, delay, etc. This makes OSPF a link state protocol designed for more robust and accurate routing decisions. And EIGRP, which was originally a Cisco proprietary, but Cisco released its details in 2013, and it stands for Enhanced Interior Gateway Routing Protocol, is kind of a bit different. This protocol is considered as an advanced distance vector protocol because it combines some characteristics of both distance vector and link state protocols, offering a balance between simplicity and efficiency. Dynamic routing simplifies network management and ensures data travels the most efficient path, even in complex, ever-changing networks. From another point of view, routing protocols are divided into IGP or Interior Gateway Protocols and EGP or exterior gateway protocols. But before we can compare IGPs and EGPs, it is important to understand the concepts of an autonomous system or AS. An autonomous system is essentially a collection of IP networks that operate under the control of a single organization or administrative entity. For example, you are the network administrator of a company A and you manage your whole infrastructure. And that infrastructure is basically an AS because it is totally managed by you. Interior gateway protocols or IGPs are used for routing within a single autonomous system. These protocols help manage the internal flow of traffic and ensure all routers inside the AS know how to reach all internal destinations. OSPF, EIGRP, and RIP are examples of IGPs, and they are optimized for speed and efficiency within the boundaries of an AS. On the other hand, EGPs are used for routing between different autonomous systems. The most widely used EGP today is BGP or Border Gateway Protocol, which is the routing protocol for internet. BGP ensures that the data can travel efficiently between organizations or networks, or basically between different AS. And it is essential for global internet connectivity, as I mentioned. Let's dive into the concept of administrative distance and how routers use it to make decisions when multiple routing protocols provide a route to the same destination. Imagine this scenario. The network 192.168.1.0/24 is being advertised by 3 different protocols: RIP, OSPF, and EIGRP. The router receives all 3 routes and must decide which one to use or install in the routing table. This decision is not based on the metrics like hop count or link cost or state, but rather than that, it is on administrative distance, which determines the trustworthiness of each source. Administrative distance is a numerical value assigned to each type of route. The lower the value, the more trustworthy is the route. For instance, EIGRP has a lower administrative distance than OSPF or RIP. So in this case, the router would choose the route provided by EIGRP. Here are some examples of administrative distances for common routing sources. Connected routes have the administrative distance of 0, which makes them the most trusted networks because since the network is directly connected, other sources cannot be trustworthy as such because router knows that this network is specifically connected to itself and it doesn't need to other people to tell it where to go to access this network. Static routes have the administrative distance of 1, which actually makes the administrator the most powerful people after connected routes. This value for external BGP is 20, for EIGRP internal routes is 90, for OSPF is 110, for ISIS is 115, for RIP is 120, for external routes of EIGRP is 170, and for internal BGP routes is 200. By comparing these values, the router selects the most trustworthy route and populates it in the routing table. Understanding administrative distance helps network engineers ensure that routing decisions align with their network design and traffic flow requirements. Let's talk about floating static routes and why they're useful in certain scenarios. Here is the situation. Imagine you have 2 links to your corporate WAN. One is a 10 megabit per second link configured with a static route, and the other one is a much faster 1 gigabit per second link, but it is managed by OSPF. Because static routes have an administrative distance of 1, which is lower than OSPF default administrative distance of 110, the router will always choose the 10 megabits per second static route, even though the 1 gig link is clearly the better option. In situations like this, we use a floating static route. A floating static route is simply a static route configured with a higher administrative distance, making it less preferred than the OSPF route under normal conditions for this scenario. In your situation, it might be another routing protocol. By assigning the floating static route an administrative distance of, say, 200, for example, for this scenario, we ensure that 1 gig link OSPF is used as the primary path. However, if the OSPF route fails, the router will fall back to the floating static route, ensuring there is still connectivity to the corporate WAN. This technique provides both flexibility and reliability, enabling you to optimize routing decisions while maintaining a backup path for high availability or redundancy. Here are two examples of a floating static routes for IP version 4 and IP version 6 default routes. For IP version 4, you can say IP route 000 space 000 and the next hop, and finally at the end, you add the administrative distance. For this case, for example, 200. And for IP version 6, we do the same. IPv6 route and default and the next hop and the administrative distance. Now let's look at the concept of the longest prefix match and how routers use it to make routing decisions. Here is the scenario. We have 3 routes in the routing table. 192.168.1.0/24, which is routed out of gig 00. 1.0/27, which goes out of 0/1, and 192.168.1.2/32, which is a host route, and it is going out of gig 0/2. Now imagine a packet arrives at the router with a destination IP address of 192.168.1.2. The router checks its routing table to determine the best route. And here is where the longest prefix match comes into play. The router doesn't just look for the first match. It's not equivalent to security devices. It looks for the route with the longest and the most specific prefix. And in this case, 192.168.1.0/24 matches the first 24 bits of the IP address. /27 is more specific because it matches the first 27 bits of that destination address. But 192.168.1.2/32 is the most specific match, as it matches all 32 bits of the destination address. Therefore, the router will choose 192.168.1.2/32 route and forward the packet out of gigabit Ethernet 0/2. Alright guys, this was our today's video. In the upcoming video, I'll be talking about OSPF basics. I wish you enjoyed today's video and see you in the next ones.